Hello, everyone. Welcome back to the channel. So today we're going to be talking about the out of Africa hypothesis. This is the prevailing view in human evolution that humans arose in Africa and then spread out across the world. I'm going to be presenting you both simulation evidence to kind of like prime your expectations of what the genetic data should look like, as well as reconstructing the genetic data for you, and then we'll walk through those results. Now, what we're going to be doing is comparing these results specifically to Rob Carter and Friends' 2018 paper published in a creationist journal that was attempting to debunk this idea that instead of coming out of Africa some 150 to 200,000 years ago, humans actually originated within the last 6,000 years and that we dispersed out of Babel. We're going to get into that in a little bit more detail, and we're going to compare these two models. But first, I want to give you the history of the out of Africa hypothesis, notably because it was first put forward by Darwin in The Descent of Man. He writes, "It is probable that Africa was formerly inhabited by extinct apes closely allied to the gorilla and chimpanzee, and as these two species are now man's nearest allies, it is somewhat more probable that our early progenitors lived on the African continent than elsewhere." Now, he will go on to note that this is largely speculation because there have been large apes found elsewhere in the world, but he was the first one to propose the idea that humans originated in Africa. Now, the idea wasn't given a lot of credence until in 1925, when the Australopithecus africanus specimen was discovered in South Africa and described by anthropologist Raymond Dart. So after that, anthropologists began searching Africa much more extensively than they had been before, and now we have found dozens of hominin fossil species, all of which are much older than those that we find anywhere in Asia or in Europe, supporting Darwin's original idea. And then furthermore, now we have the genomes of thousands of individuals all around the world, and we're able to find that the oldest lineages consistently converge in Africa. This is a paper from 2022 called A Unified Genealogy of Modern and Ancient Genomes. They use over 3,000 whole human genome sequences, as well as several ancient genomes, and they can very clearly root the human genetic pedigree in Africa over 200,000 years ago. Now, despite this overwhelming body of evidence, there still persists a minority opinion among creationist groups that humans originated much more recently and that they did not originate out of Africa, but yet they originated in the Middle East, and that all ethnic groups come from out of Babel story. And we'll talk about that story in just a moment, but this is the paper that we're going to be comparing our out of Africa model with specifically. It's by Rob Carter, Stephen Lee, and John Sanford. What they do in this paper is they reconstruct basically the human Y chromosome and mitochondrial genomic sequences to create these kinds of like unrooted, bursty trees. I was very curious as to why they chose this form of plotting, and we'll get into that in a moment. But yeah, this is the way that they chose to plot the data. And they write the general pattern of what we see in their analyses support a primary dispersion of humanity in the recent past, and that they call this the out of Babel hypothesis. So let's look at their abstract, and we're going to address three of their major points, and we're going to see if they're interpreting their results in a reasonable way. So starting here, first, the pattern displayed in both data sets, that is the Y chromosome and the mitochondrial, supports a massive expansion of the human lineage, with multiple new branches forming from closely related individuals. Now, this is what they're talking about here. They're talking about these nodes that you see down here in the tree as representing individuals that are closely related in their estimation, such that all of the following haplotype diversity that you see expands from them. Okay, that's their first claim. So that each of these individuals are basically contemporaries. To them, they are Noah and Noah's children, effectively, right? Second, for both chromosomes, the mutation rate along each branch has not been the same through time. They also state that all of these individuals, oh, wait, this is the third thing. So third, both phylogenetic trees display a starburst pattern that centers around specific historical individuals, nearly all of whom lived in the Middle East. Again, I don't know how to address these individuals living in the Middle East, because these aren't actually individuals that you sample, they're individuals that you reconstruct. And in their original study, they didn't do any kind of like spatial reconstruction of ancestral nodes. So I don't know how they inferred that they were Middle East individuals, because these lineages out here that you see are actually all African individuals, which means that this individual was an African, as was this one actually, because this is also Africa. So it's unclear to me how they inferred that that was Middle East, but again, we'll get into that in more detail. And the starburst pattern, that is right, effectively all of these things kind of like burst out from the center. That's what they're interpreting as a starburst pattern. So this is the story of in Genesis about Babel. I'm just going to read you really quickly this particular story, just in case you're not familiar with it. And the whole earth was of one language and of one speech. And it came to pass, as they journeyed from the east, that they found a plain in the land of Shinar, which is today this region here along the Euphrates, that includes Babylon as well as some neighboring ancient cities. This is the inset here, so you can see it's just north of the Sinai Peninsula, southeast of Turkey, modern day Turkey. And they said, "Go to, let us build us a city and a tower, whose top may reach unto heaven, and let us make us a name, lest we be scattered abroad upon the face of the whole earth." And the Lord came down to see the city and the tower which the children of men build. And the Lord said, "Behold, the people is one, and they have all one language, and this they begin to do. And now nothing will be restrained from them which they have imagined to do. Go to, let us go down, and there confound their language, that they may not understand one another's speech." So the Lord scattered them abroad from thence upon the face of all the earth, and they left off to build the city. Therefore therefore is the name of it called Babel, or Babel. I don't actually know how to pronounce it correctly, but because the Lord did there confound the language of all the earth. So again, to them, this is the origin of all languages, all ethnicities, etc., is this particular event. So to them, this is the origin of humanity that then spread out across the world. It doesn't seem like a very good tactic, in my personal opinion, because while maybe they could not understand one another's speech then, we can speak multiple languages today, and it seems like very easily now we can overcome this once terrible curse that prevented us from building a tower to God. I don't know. It doesn't seem like a very like a like a very good curse if it can just be overcome with a dictionary. I digress. Okay, so ultimately, out of Africa or out of Babel. So this is our approach. First, we're going to evaluate Carter's interpretation of this starburst pattern. And we're going to do that using neutral simulations. We're going to effectively run some simulations, and we're going to construct our phylogenies unrooted, just like they did, to see if we can get the same starburst patterns without having like a massive population bottleneck like Noah's Ark would suggest. Secondly, we're going to evaluate how founder events actually shape phylogenies and diversity using simulations to sort of prime our expectations about how the empirical data should look. And then finally, we're going to generate our own phylogeny using human mitochondrial DNA under a Bayesian statistical approach. And I'll go through that in a little bit more detail, what that means whenever we're actually doing it. Note that all simulations are performed in SLIM 3. This is the citation for that. This is a freely available simulation software, and I will provide all of the simulation code on my GitHub that's linked on my YouTube page. Okay, so can we generate a starburst pattern from a neutrally evolving population? So I set up a simulation. I generated a continuous landscape. That's what you can see here. All these little dots are individuals on our landscape. Individuals mate with only those that are closest to themselves, so there is spatial structure. They're not just mating randomly. There's density-dependent selection that constrains population size, which means population size is not constant. It varies based on density-dependent selection. In this case is sort of like there is a carrying capacity so that the environment can withstand. So it can only sustain X number of individuals before you exhaust the resources. So that's basically how the simulation's set up. And then I'm going to output the entire population phylogeny at the end of the simulation, and I'm just going to display it in a couple of different ways so we can see what it looks like. So importantly here, this is a neutral simulation in that there's no selection, there's no population bottlenecks, there's no population expansions. It's just a stable population with some continuous structure in it, and that's basically it. And these are the two ways that you could display it. So on the right, this is like what I think is the more natural way of displaying the tree, because these nodes do actually exist. There is actually a rooted structure to any genealogy, right? And you can see that most of the coalescence happens very, very rapidly towards the beginning, with the branches getting longer and longer and longer and longer as you go backwards into the past. And then the longest to, like maybe half of the tree is represented in the last 4 nodes, right? Now, when we plot this in this kind of unrooted fashion, like how Carter and them do, you can see that we can completely recapitulate a starburst looking pattern, right? It looks like, in the way it's being plotted, that you could say maybe this one, this one, this one, maybe these few individuals could be like Noah's children, right? And they're giving rise to all the different people groups. Now, when you plot it like this, you could make that argument. But when you look at the way the phylogeny actually exists, you can see that there is a massive distance between each one of these nodes, right? That these individuals are not contemporaries, right? They lived a very, very long time away. For them to be contemporaries, they would need to be aligned along like a single axis, not spread out across the X. And so I'm just putting this neutral simulation with no bottleneck against their 3 trees to show you that the starburst pattern is apparent in all of them. The only main difference that you're seeing is these longer branches. Notice, interestingly, that they don't label the geographic location of these branches. We're going to get to that. But just keep that in mind, that they don't tell you what these branches are, other than claiming that they have faster mutation rates. So just keep those branches in mind for a moment. But other than those really weird long ones, all the rest of the starburst pattern we can see is completely recapitulated in a neutral simulation with no bottleneck, right? Okay, so how do founder events shape phylogeny? So this is important before we get into the empirical data to kind of understand what we should expect, right? And importantly, colonizing new areas results in a founder effect. And this is a reduction in diversity in the founder populations relative to the source population. So if this is our source, and then these smaller circles are the founders, then you have just a subset of the source coming out and founding a new population. So with each successive founding event, you have a smaller and smaller subsample, and so diversity is just smaller in them, or just lower in them. So individuals in the founder populations are more related on average than they are to the source population. Source populations, therefore, have longer branches than the founder ones. What we mean when we say longer branches is more diversity, right? Because diversity arises through time along the branch of a phylogeny. If you can imagine a phylogeny as a continuous link with, every step being a generation, the mutations arise along that branch, right? And that's what if we go back here, that's what these branches are representing. So these are the actual population phylogeny. I didn't reconstruct these from mutations, right? This is the true time to each ancestor. So if I were to then put mutations, if these individuals actually had variants, then they would have arisen along these branches. So the longer the branch, the more mutations these individuals down here would have relative to how many these down here had, okay? So that's what I mean when I say longer branches are actually reflecting greater diversity. Okay, so founder populations finally should nestle within source population phylogeny. So since each one of these founders are arising from a source population, right, the source population is necessarily going to be related to the founders, and some of the individuals in the source are going to be more related to the founders than they are to other individuals from the source population. So you're going to end up getting a phylogeny that looks like this. We've got some founders. Let's say these three are founders, and then you have one individual in the source that's more related to them. Let's say these original founders were the cousin of this individual, whereas these two individuals are more distantly related. So you're going to get a phylogeny where the founders are nestled within the source population. Okay, so let's then set up kind of an arbitrarily complex simulation model where we can see if we can recapitulate that kind of pattern. So what I did is we're going to start on this side. This is the little landscape I sort of put together. This is just a cartoon of it. And I had a large ancestral population with some spatial structure between it. So there's these arrows represent migration between each of these little populations. These are areas that can be colonized but are not yet colonized. Okay, so we let the model run for a while with just this population, and then we allow some individuals to come over here and found this population, but it's just a small number of them. They don't initially fill up the landscape, but then over time, they slowly expand to fill the landscape, right? And then eventually they also migrate to the final area, slowly expand and fill it. So that's the way we're setting up our population model. It's not exactly an out of Africa model, but I think it pretty closely captures the kinds of dynamics that we would be thinking about in an out of Africa sort of model. So these are the results from that. I've colored red everything that's the source. That's the original three little populations. This is what the simulation model actually looks like. I just think it's ugly, is why I showed you the other one. But here's the original three, and then these are the two founders. So the source is colored in red. That's these individuals here. And then notice that you've got source here and here. These are individuals that are from the source, but they're more related to the founder populations than they are to the other sources, right? So note that the founders have very short branches and that they are all nestled within the source population. Right? They look like they arise from within the source population. Now, this is exactly what I was showing you before, that the founders are not going to be like reciprocally monophyletic with the source. They're going to appear from within it. Okay, so now that we've looked at all of that, let's see if we can actually find a similar pattern using human mitochondrial data. So what I did is I picked this paper called Mitochondrial Genome Variation in the Origin of Modern Humans. You'll notice this guy here is actually the one that this past year won the Nobel Prize, pretty excitingly, for his work on Neanderthal sequencing. But there were 53 whole mitochondrial genomes that I downloaded from NCBI. NCBI is a freely available public database. Anybody can use it. You can get on and download these exact same sequences. I aligned them using an online math tool. Again, this is a free software you can use online. I applied to them a GTR nucleotide substitution model. I'm going to go through all of like the complexities of this just to like be as obvious and clear as possible with what I'm doing. If some of this seems very obscure, it's because this is something that Carter and them didn't do. They didn't use like a very sophisticated model to reconstruct their phylogeny. And so I just want to be as clear as possible. And so I'm going to use all of the phylogenetic terms, and hopefully I don't lose anyone, but I'll try to briefly describe what each of them means. So this is just the rate at which any given nucleotide changes to another. So A to a T to a C to a G, and back and vice versa. The GTR just allows them to change to any other one at their own rate. So the rates are all independent of one another. I apply an exponential coalescent tree prior. We do this because we expect that human population size has expanded, right? That's something that we have prior knowledge on. We expect that has occurred. And so that what it does is it assumes that at some point in the phylogeny, there may have been a period of exponential growth. Now, if it doesn't detect it in the data, it won't infer it, but it gives it the option to detect that if the data suggests it. Importantly, I then also apply a local random clock. Very often I see people saying that we always have to assume a strict molecular clock, and that's just not true. We have so many other models than strict molecular clocks. In fact, you very rarely see phylogenies built using strict molecular clocks anymore. So I'm using here a local random clock, which means that the clock rate for each and every branch is estimated independently. I give it a mean. This is 1.7 e to the negative 8. That's the empirically estimated mutation rate. But I give it an infinite confidence interval, negative infinity to positive infinity. So the model can literally search the entirety of parameter space to find the best fit for the model, right? It does not have to assume that rate is true everywhere in the tree. That's very, very important. The MCMC, this is how many runs the model performs. So I performed it for 10 million generations. This gets a little bit into the weeds, but an MCMC is a Markov chain Monte Carlo. It's a part of Bayesian statistics where you're constructing the model in step one, calculating its by constructing it, I mean constructing the tree, all the parameters that control how the topology of the tree, the branch lengths, et cetera, all the different rates that I was just talking about. It estimates all of that in step number one. Step number two, it does it again, changing things a little bit, retweaking things, moving stuff around, just jittering with stuff, and then it compares the probability of number two to number one. If number two was better, then it throws out number one, and number two becomes our new tree. And then it just does that again for 3, 4, 5, 6, and it does that 10 million times, right? And the idea is that after doing that 10 million times, you should begin to converge on the best answer. And that the step-by-step variation shouldn't be so high that you're still jumping around a lot, right? Maybe that's too much into the weeds, and I hope I didn't lose anybody there. But I just kind of want to be very open in how I'm constructing this phylogeny. And then I looked at how that MCMC was performing using tracer. I'm going to actually show you some of those plots in just a moment. And then a consensus tree was generated to evaluate the support for the nodes. And then we just kind of visualized it using fig tree. So BEAST2, Bayesian evolutionary analysis by sampling trees. This is the program that I use to build these trees. Okay, so let's have a look at some of the output. Okay, so first off, this top plot, these are the estimated rates across the entire tree. So like I said, I allowed it to estimate the substitution rate on the whole tree, not assuming a constant rate at all. And you can see that the rates are variable, but if you look close, these are bar plots, and there's a little dark line in the middle. Those are the medians, okay? Those are the values we care about. Everything else, like the straight lines, these are outliers. Everything in here shows you a little bit more of the range of variation, but the dark lines are really what we're going with. Those are the medians. And you can see those are not very variable. Okay, but it's important to note that while I'm using the word substitutions per site, this is a population. It's not a phylogeny of different species, okay? Normally, substitutions are referring to fixed differences between tips, right? And that is to say fixed differences between species, but this is a phylogeny of population. So by necessity, all of the differences between individuals are not fixed. These are polymorphic, okay? So we're not quite talking about the same thing as what we would be talking about when we're looking at a phylogeny of different species. I just kind of want you to keep that in the back of your head. Okay, so down here, we're looking at the rate. These are the rate estimations for the different, for the GTR model. So the change of A to C, A to G, A to T, C to G, G to T. And you can see for each one of the colors, most of the rates were estimated as very, very low, with the one exception of A to G transition. These are purine-purine transitions, are far more common than all other mutations. And this is, I've seen this in basically every data set I've ever looked at. A to G transitions, because they're purine-purine changes, are just incredibly common. But yeah, there's just you can see that the model recognized that, and it estimated that rate of change as being faster than all other transitions. Okay, so the results for here mixed somewhat poorly. And what that basically means is that you can see there's like several little bumps, and like this is not a very smooth curve. Ideally, what you would do is run this model for more generations than 10 million, maybe run it for 100 million to see if you can get a smooth curve. But I ran this like on my local computer, so I didn't want to run it that long. But just kind of like give you an idea of what this looks like. But you can notice that this is the growth rate, the population growth rate along the x-axis here. At 0, that means that there was no population growth. Below that, there's negative growth, and above it, there's positive exponential growth. And you can see that there's very good evidence, the highest posterior densities right through here for an exponential population growth for this data set. And we also estimated that the population size, the exponentially growing population size, is around 30 million individuals. And I think this is a pretty reasonable number for human population sizes during the period of exponential growth that would be captured in genetic data. And then the last plot that I want to show you here is the highest posterior density. That's what these HPD stands for the tree height. So you can think of this as the most recent common ancestor of all humans in our data set. And it occurred sometime between 150 and 210,000 years ago. That's where the most of the data fell, or most of the models converged on that number. You've got a couple little spatterings out here, but clearly this is the most supported region. And it's nice because this is the timing that has been estimated in a ton of other studies as well, right? This at least tells us that our model is producing reasonable results that are in line with other studies. I didn't just like completely muck this up. Okay, and now this is our consensus phylogeny from the mitochondrial data. And I want to walk you through all of the bits and pieces of it. So first, I've color-coded based on geographical origin. So all the individuals in red are from Africa. This green is Asia. South America is the yellow. Oceania is this lighter blue. Purple is the individuals from Europe. And then this sky blue are the individuals from North America. Second, notice that the x-axis is scaled to time, and it goes back just over 175,000 years ago. So this is our root right here, just under maybe 174, 173,000 years old. Each of the nodes are marked by what's called the posterior probability. That's how likely it is that node, or how frequent that node was found by the model. You can think of it as a measure of node support, right? So everything with 1 means that we found that in every single reconstruction, every single model converged on that node existing. Anything less than like 0.9, you start to be a little suspicious of. So like these two here, for example, 0.28, 0.26, you would just collapse these. So instead of like having this branch exist, I would just remove it and collapse it down. Same thing here, remove this split, collapse it, and then I would just have a polytomy right here. That's normally how you would do it if you were presenting it to a journal. What else? So I've also added a little red star right here. This represents the out of Africa node, because everything from here up is either African, like these individuals, or they are individuals that are out of Africa. Right. Now, you note that I can't move it here or to here, because to move it here would be excluding these non-Africans, and to move it here would be excluding these, right? So this is the only one that includes all of the individuals that have migrated out of Africa. This also tells us something very interesting, is that these African populations, all the ones up here, are actually more related to individuals from other parts of the world than they are to other Africans, right? So that's one interesting thing that we immediately can see from this phylogeny. And the second one is that notice how all of these out of African populations cluster or clump within the African groups, right? So this is just like in our simulation model before, where we were seeing the source and the founders, our founders are here clustering right within our source. So I'm just going to put those two side by side. This is the simulation model where you had the source had the greatest diversity, longest branches, and then the founders clustered within it. Just like here, the source has the longest branches, the founders cluster within it. Now, let's look at our tree if we were to try to construct it in the way that Rob Carter and friends did. So you can see that the tree is basically the same. They have more tips than we do because we only have the 53. I don't remember the number that they actually subset by, but they didn't actually use the whole 1,000. But regardless, they have more tips than we do. But notice how, one, they don't label where these groups are from. Right. So you don't know where the geographic location of any of these individuals. Only since we know these can we say that these individuals are all African, right? Because we actually have the tree here. So we know that this is an African branch, this one here. We know that all of these are African branches, which are these here. And then these branches are the out of African populations through here. So when you ask the question, well, why is it that these have such longer branches? Could it be that the mutation rate here, and their argument is that the mutation rate is higher here, but remember, in our simulation, these are the ones with the longer branches, but the mutation rate's constant. There's no changing mutation rate. What's changing is the demography. These individuals are going through population bottlenecks. So they just have less diversity than these individuals. The same thing here. This is not the case of variable mutation rates. Again, we showed the mutation rate is not that variable, right? There's not a ton of variation here. And yet we see differences in the length of the tree. And we know that that difference is because of demography. These individuals are the older lineages that did not leave Africa, whereas the lineages that did leave Africa, these down here, have a lot shorter branches. Also note that the timing between these nodes. So one of the things that they said was that these nodes represent historic individuals like Noah's family that would have all been living at the same time. Let's go back here. These are the nodes they're talking about. These. Notice how distant those nodes actually are to each other. This node is what, maybe 85,000 years ago, and it's separated from this node by 40,000 years, which is separated from this node by 60,000 years. Do you see what I'm saying? That these nodes can't represent what they're claiming it does. It doesn't make any sense. They're not contemporaries, right? They're definitely not contemporaries. Okay, so in summary, we showed that the neutral simulations demonstrate the starburst pattern that Carter et al. Rely upon, that it's just a side effect of how the data is being plotted, right? Since our neutral simulations also look like starburst, and their empirical data look like starburst, it's just because we're plotting it this way. It's obscuring the internal branches, not because the starburst pattern is actually telling you something about the data or about demography. Founder simulations demonstrate source populations have greater diversity than their founders. This is kind of like basic pop gen, right? And that founders generally nestle within source clades. We find that human substitution rates are variable, but they're not dramatically variable. The highest statistical support for the most recent common ancestor of humans based on the mitochondrial data is 150 to 210,000 years ago. And that human mitochondrial DNA phylogeny resembles the founder simulations, with African populations having greater diversity and others being nestled within that population. So again, we have here shown that Carter and friends are, one, plotting their data in a misleading way that's not actually showing you, like, one, where those samples are coming from, and two, the relationships between those internal nodes, just how much distance there are between those internal nodes. And speaking of this plotting, I think it's important to note that the program that I used to construct this tree, Beast, roots it itself. I did not root that tree. That tree is rooted by the model itself. It tries to find what is the best root for that tree. So it completely removes any like human bias in rooting the tree. The model itself searches for the best root. Um, yeah, and I think we've shown very clearly that all of the out of African populations cluster within the African populations exactly as we would expect in an out of Africa model. Not at all what we would expect in a sort of out of Babel or out of Babylon sort of model, right? If you have any questions, leave me a comment, and I'll be happy to answer them as best as I can. Thanks for being here, and I'll catch you next time.